Hello everybody, and welcome to our class video about how to evaluate a limit analytically. Our learning goal for this video is that you will be able to apply algebraic methods to evaluate a limit. So let's get started, shall we? Depending on when you're watching this video and whether you're getting ahead from where we are in class or not, chances are we've already talked about how to evaluate a limit in two different ways. We're going to add a third today. The first way we've already talked about is graphically. So we have a function, and as x approaches a certain value from either side, if y approaches a certain value arbitrarily close, then we say the function has a limit of that value. We've also talked about how to evaluate a limit numerically, that is with a table. So I choose some numbers that are really close to a specific x value on either side, and I observe the values of the y's. If they approach, or become arbitrarily close to a specific value, as x approaches 2 in this case from either side, then we say that y would have a specific limit. Okay, this function has a limit of 4 as x approaches 2. Right? Then also, what we're going to cover today is how to evaluate a limit analytically, that is, using algebraic techniques. Okay? Don't be worried if you don't understand that right there. We're going to cover it in just a second. Alright, so let's talk about how to evaluate analytically. Our first strategy, method number 1, is to try direct substitution. This is the one you always try first because it's simple and straightforward and easy, and if it works, then great, you don't have to do any more work. Okay, so let's try the limit as x approaches 0 of x squared minus 3x minus 4 all over x minus 4. Okay, so when I say direct substitution, what I mean is just try plugging in the value that x is approaching. Let's try plugging in 0, see what happens. Okay, so in the numerator, I plug in 0. I would get 0 squared minus 3 times 0 minus 4. And let's see, that all evaluates to negative 4. Great, let's plug in 0 on the bottom. 0 minus 4 would also be negative 4. Okay, so as x approaches 0, this function would have a value of negative 4 over negative 4. Well, I know what that is. That's 1. Okay, great. We evaluated the limit. That was pretty straightforward, huh? So if the limit, if we can plug in the value x is approaching, we can get a quick answer. Let's look at what this looks like graphically. Okay, here's our function. As it turns out, if you graph it, it looks like a straight line. In fact, just like the line x plus 1, but it has a hole at x equals 4. Okay, so if we observe as x approaches 0, so I guess I don't really care about the hole. I'm way far away from it. Okay, so as x approaches 0, what's happening to y? Well, it looks like y is approaching 1. So there we go. The limit as x approaches 0 of that function would be 1. Let's look at it numerically. Okay, so I would want to choose values very close to 0 on either side when we're talking about x. And so here are the y values associated with those. Notice they are very much like the function y equals x plus 1. Okay? So we want to look at, as x approaches 0, what happens to y? Well, it looks like the y values are approaching 1 from either side. So hence the limit value would be 1. Alright, so now just pretend with me for a moment that the actual function value at 0 was 3. So instead of having that, if you look at the graph over there, instead of having the value at 1, the function is discontinuous and actually has a value at 3. So the y value there on the table, we changed the 1 to a 3. Let's just what if, okay? So in that case, the limit would still be 1 because I'm just looking at what happens to y as x approaches 0, but not actually at x equals 0. In other words, who cares what that function value is? What I'm looking at is what's going on with y around it. Okay, so I'm looking at what is y doing as x approaches 0 from either side. Alright, so Now then, let's look at one where direct substitution will not work. In this case, we're going to try a second method called factoring and canceling. Okay, so let's consider now the limit as x approaches 4 of the same function. Okay, same function we were working with before. All right, but now, before we try anything else, we want to try direct substitution to see if we need to do another method. Okay, so let's try plugging in 4. All right, so in the numerator, 4 squared minus 3 times 4 minus 4. So that would be 16 minus 12, that's 4. 4 minus 4 is 0. Great. Next, on the denominator, 4 minus 4 would be, well, 0. So this limit would evaluate to 0 over 0. Huh? What's that supposed to mean? I don't know how to do 0 over 0. As it looks to me, 0 over 0, there's 3 different rules that all seem to apply at once. One is that my elementary teacher, school teacher, told me that 0 divided by anything was 0. Well, okay, but then later on I learned in math that anything divided by 0 was undefined. And then I also learned back in elementary school that anything divided by itself was 1. So what's the answer here? Well, it turns out that 0 over 0 is something called an indeterminate form. We use that to mean that it really tells us nothing. The fact that we get 0 over 0 tells us absolutely nothing about the answer. It could be 3, it could be 5, it could be infinity, it could be who knows. We have no idea. Okay? If you want more information about what 0 over 0 really is, just ask me in class and remind me and I'll tell you guys. Okay? So, we need to try a different method. But notice first, before I go on, that I did not put equals 0 over 0, because that would be an incorrect statement. A limit can never be equal to 0 over 0. If you put equals 0 over 0 on the AP test, they will dock you a point, or at least they could. You don't want to trust that the grader's going to have a good day. Okay, so never put equals 0 over 0. You can put 0 over 0, just don't put equals 0 over 0. Okay, all right, let's get rid of that. So let's look at limit as x approaches 4 of this function. All right, so our method we said was factoring and canceling, so let's factor. So if I factor the numerator, I would get limit as x approaches 4. Yeah. Make sure you always write the limit as x approaches 4 again, because if you don't put that limit there, then again that becomes a false statement and the grader could dock you points. All right, so if I factor the numerator, I would get x minus 4 times x plus 1. If you need a refresher on how to factor, if you've forgotten, hopefully it's been ingrained into you up to this point, but I will give more detail on factoring in the next example, or you can always ask me for help and I will be more than happy to help you practice factoring. All right, so in the denominator, no factoring to do there, it's still x minus 4. Okay. Oh, look, I have an x minus 4 in the numerator and in the denominator, so I can cancel them. So, poof, they're gone. So, I now have limit as x approaches 4 of x plus 1. Notice again that I still wrote the words limit as x approaches 4. Okay. So, now that I've canceled those, I can apply direct substitution. I can plug in the 4. If I plug in the 4, I get 4 plus 1, which is 5. Great, I have evaluated the limit. That limit is equal to 5. Okay, before we go on, I want to point out some other technicalities on which you could lose points. Here, let me speed that up a little bit. Okay, so here are some things not to do. Okay, here, I write the limit, okay, and we just say that's equal to what I factored it to. What did I leave out? I left out the words limit as x approaches 4. Okay? If you leave that out, that is not true, because that limit is a number. It cannot be equal to a function. Doesn't work. Don't do that. Always make sure you put the limit in between. Okay? Another thing that you can do wrong is to say this. Well, I mean, that seems to be true, right? However, that is not a true statement. Those two functions are not equal, so you cannot say they are equal. Their limits are equal. If you look up here, okay, you see that the limits of those two functions are equal, but the functions themselves are not equal. You could, however, say for x does not equal 4. If you say that, then you're okay. But why bother? So so these functions are the same except for when x is 4, because x cannot equal 4 on the left function. Okay, so moving on. Let's look at this previous problem graphically. So we're looking at our function x squared minus 3x minus 4 all over x minus 4, and we're looking at the limit as x approaches 4. Okay, so as x approaches 4, if we look at the graph, what is y approaching? Well, if I kind of draw on the rest of the little marks there, we see that y is approaching 5. Now, this also is confirmed by the fact that we know that this line is equivalent to the line y equals x plus 1, but all except for at the actual point at where x is 4. Okay, numerically, okay, let's look at a table. So I would want values close to 4 on either side on x, and here are the y values associated with them. Again, look how y is just x plus 1. Okay, so looking at it on the table, as x approaches 4, then what is y approaching? Well, it would appear from looking at the blue numbers that y is approaching 5. Again, remember that for the fact that plugging in x equals 4 would produce an error in your calculator, then who cares what that is? All we care about is that y is approaching 5. Okay, so let's look at one more example. Let's consider the limit as x approaches negative 2 of 2x squared plus x minus 6 all over x squared minus x minus 6. I specifically chose this example because it's going to require us to factor something that's a little more complicated, because then on the numerator I have a coefficient of x squared that is greater than 1. Okay, so this is where I'll slow down and do a little bit of more focus on how to factor. But if you think you got this, okay, then why don't you pause the video right now, try to evaluate that limit, and you compare your answer to mine. Alright, you done yet? Okay, so let's first try direct substitution, as we always need to do. So let's plug in negative 2 for x. So here I have done that. So 2 times negative 2 squared. Tell you what, you check me on it. It evaluates to 0. Okay? So then on the denominator, plug in negative 2. That also evaluates to 0. Again, check me if you don't believe me. Okay? So this limit would result in 0 over 0. Because of that, I can't go forward unless I do something else. So let's factor the numerator and the denominator. I'll factor the simple one first. So when factoring with a coefficient of x squared that's 1, okay, I need to find two numbers that multiply to the constant term, that is negative 6, and which add up to the coefficient of the x term. Okay, so I need to find two numbers that multiply to negative 6 and add to negative 1. Those numbers would be negative 3 and positive 2. Negative 3 times 2 is negative 6, and negative 3 plus 2 is negative 1. Once I have those numbers, I just stick them in to a form like this, and voila, I have factored. Now, what probably you all need more review on, because you've had a whole summer to sleep, is how to factor when the coefficient of x squared is not 1. If you do 2, so when you have a coefficient that's not 1, you need to multiply the first term with the last. Okay, 2x squared times negative 6 would be negative 12x squared, and I'm going to look for factors of negative 12x squared that would add up to my central term of positive x. Okay, those factors that would multiply are listed here. It would be 1x and negative 12x, 2x and negative 6x, 3x and negative 4x, and so on. All of those would multiply to be negative 12x squared. I need to pick the one that adds up to positive 1x. Alright, so see which one that is? That would be this one right here. 4x plus negative 3x would be positive 1x. That's the one I'm interested in. I prefer to use an area model when it comes to factoring this, so I'm going to put them into boxes as so. You can also do a method called factoring by grouping, which I just don't like it as much, but hey, it's perfectly mathematically valid. You go for it if that's how you learned it and that's what you like. Okay, so in this area model, I first need to pull out the greatest common factor of one of the rows or columns. The greatest common factor of the top row, okay, is 2x. Both terms are divisible by 2x. Once I've done that once, I just need to then figure out what the other sides of the box are, so that way each term multiplies to give me the area inside. So if you consider on top, that term would be x, because 2x times x is 2x squared. On 4x, okay, that term above there must be plus 2, because 2x times positive 2 would be positive 4x. Down below we must have a negative 3, because negative 3 times x would be negative 3x, and negative 3 times positive 2 would be negative 6. So, voila, here are my two factors. Okay, hope that refreshes your memory enough. Let's finish this out. So, this limit must be equal to the limit as x approaches negative 2 of 2x minus 3 times quantity x plus 2 all over quantity x minus 3 times quantity x plus 2. Ah, I see what we can cancel. And poof, it's gone. The x plus 2's cancel. So, now that I have that, I now have this limit. The limit as x approaches negative 2 of 2x minus 3 over x minus 3. Notice I'm writing the word limit as x approaches 2 each time. Alright, so now I can actually plug in the negative 2. Okay, so 2 times negative 2 minus 3 over negative 2 minus 3. Okay, the numerator would evaluate to negative 7. And then the denominator, negative 2 minus 3, would be negative 5. So it would come out to 7 over 5. There we go. That limit evaluates to 7 over 5. Whew. Okay, so I think that's enough. And now it's time to make my exit, since this video is concluded. And so, let me entertain you with a little magic. Now you see me, and poof! Now you don't.